Alright gang, here we go. So this is Chem 1, Unit 4. We're going to be talking about VSEPR theory. Alright, VSEPR stands for Valence Shell Electron Pair Repulsion Theory. Alright, valence shell electron pair repulsion theory. So we're talking about valence electrons, they're creating shells, and the electron pairs are repulsing one another. Essentially what it allows us to do is predict the 3D shape of a molecule. So by looking at VSEPR theory, we can say, oh, that thing in 3 dimensions is going to be this kind of shape or this kind of shape, whatever. Okay, and essentially this occurs because our central atom is surrounded by either lone pairs or bonds, right? Double, triple, single, it doesn't matter. Okay, and these electrons that are making up these either lone pairs or bonds are all negatively charged, right? And since they're all negatively charged, that means they push each other away or they repulse each other. It's like, hey, I don't like you, you're repulsive, right? And so they push each other away. Okay, and so when that happens, they're going to always separate out to be as far apart as possible. Now, because they're going to do that, they're always going to make very predictable shapes, which is super nice. All right, one thing that you need to know is that lone pairs always take up more space than shared pairs, and that's going to make a little bit more sense here in a second. Okay, and it's really not that hard, to figure out VSEPR theory, especially with the chart we give you. Okay, so the first step is to always draw the electron dot structure. If you draw the electron dot structure, you're good to go, and then from there we can determine the geometry. All right. So the chart you're going to use, you're going to get a hard copy. All right. And then this is the chart here. Okay. So essentially what you're going to be doing is looking at that central atom in your electron dot structure, and you're going to be counting up. First, count up the number. All right. So we'll say this is step 1. Count up the number of electron pair regions. All right, so how many lone pair regions does it have? How many bonding regions does it have? Okay, and then you're looking at bonding pairs, okay, versus lone pairs. All right, this column plus this column should always equal the first column. Okay, so you're going to be looking at, well, how many total electron pair regions does it have? Does it have 2, 3, 4, 5, or 6? Okay, does it have, how many bonded pairs does it have? Are all of my regions bonding regions, or are all of them lone pair regions, or are they a mix of the two? All right, and then all you have to read is just this part over here. So for example, if there are 3 bonding regions, or if there are 3 electron pair regions and all of them are bonding, so it'd be 3, 3, so that means your molecule is trigonal planar, and each of these guys are 120 degrees apart from one another. All right, yeah, pretty exciting stuff. Okay, so here we go. We're going to do a couple and then we'll be done. All right, so CO2. So first we got to draw the electron dot structure for CO2. Okay, so we've got carbon and we got 2 oxygens. All right, we're going to add those guys up. Carbon is in 4A, so we got 4 carbons. Oxygen is in 6A, so we got 2 of those. All right, so that means we've got 12 plus 4, so we've got 16 electrons to work with. All right, carbon is more or less electronegative than oxygen, so we'll put carbon in the middle. We'll attach the oxygens to it, and then we're going to give everybody a full octet. 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6. All right, count these up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Whoa, we've got too many lone pairs. Okay. So that means we got to change these out. So we could so carbon dioxide's actually got a bunch of resonance structures. We could go ahead and practice those. So first, let's see. So we need to get rid of 4 lone pairs, right? So we'll get rid of these guys, and then we could have a double bond on either end, right? Where'd my pen go? There it is. So we got a double bond. All right. So that's one electron dot structure for carbon dioxide. You could also imagine that if one side had a triple bond, one less lone pair, and the other one had 3 lone pairs, that'd be the exact same thing, right? So we could do that as well. So it'd be like this, and then 1, 2, 3, and then carbon, and then 1, and then 1, 2, 3, 4, 5, 6, right? That would be a resonance structure, and then we could do the same thing, but on the opposite side. So it'd be 1 carbon triple bond oxygen, and then 1, 2. And then 1, 2, 3, 4, 5, 6. Doesn't really matter where we put that guy there, but if we don't put it on the right side, it's not going to be, oh no. Oh no. All right, well, let's do that again real quick. So we've got, there's no undo function. So here we go. We got double bonded oxygen, and then 2 lone pairs here and here. All right. And then the next resonance structure, would be like this: 1, 2, 3, carbon, single bonded, 1, 2, 3, 4, 5, 6, and then 1, 2. And then the last resonance structure would be like this: one single carbon, triple, oxygen. There we go. All right, we're back where we started, and I did it right this time. All right, so valid resonance structures, electron dot structures. Now we got to figure out the geometry. So how many, we look at our central atom, and we ask ourselves, how many electron regions do we have? Well, let's see. So electron regions, well, around the carbon, we've got 2 electron regions, right? We've got this one here, and we've got this one here, right? And it's the same thing for all of these, which is really nice. We've got 2 electron regions, right? So we've got, for our first column, we're looking for a 2, okay? So so this is the region we're in right here, this guy right there. So we've got 2 electron regions, okay? Now we have to ask ourselves, all right, how many of them are bonding regions? Well, both of them are bonding regions, and I know that because I only circled bonds, right? So it'd be a 2, 2, all right? And how many of them are lone pair regions? Well, none of them, right? I didn't circle any lone pairs, so it'd be a 2, 2, 0. So we find 2, 2, 0, okay, and so therefore it has to be this guy, which is linear. So therefore carbon dioxide is a linear molecule. Okay, all right, let's try this guy here. Chlorate. All right, so we got chlorine. Maybe I should go back to red, otherwise it might confuzzle people. So let's be careful and only click that one. And then we'll pointer options, pen, and then pointer options, color. We're going to go back to our red, all right? So we'll find our chlorine, and we've got 3 oxygens, all right? So chlorine is 7A, so it's got 7 valence electrons. Oxygen's got 6, and there's 3 of them, all right? So 7, so 3 times 6 is 18, plus 7 is 25, right? So it's got 25 valence electrons, but then this minus charge means we're going to have 1 more, so we're going to add 1 more electron. Okay, so that means we're going to have 26 electrons to work with, all right? And now we're going to draw our guy here. So now we got to think of ourselves, all right, which one's more electronegative, oxygen or chlorine? Well, chlorine is actually more electronegative than, or less electronegative than oxygen, so we'll put chlorine in the middle. And then we're going to put our oxygens all around here, all right? And then give everything a full octet, so 1, 2, 3. So now oxygen's got 8, and then now chlorine does, and that oxygen does. And my last oxygen here has 8 as well. All right, so now we got to count up our total number of electrons we used in our electron dot structure. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Awesome. So we used 26 electrons, and it had 26 electrons to work with, so we're golden. And remember, because it's an ion, we're going to put that bracket with that negative charge there. All right, so let's just double check here, because I'd feel really stupid if I screwed this up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, 26 electrons. So now we have to figure out the VSEPR, right? So now we're going to look at it, all right? Looking at the VSEPR, so we find our central atom, that's the chlorine, and we're going to circle all the electron pair regions. So we got that region, we got that region, we got that region, we got that region. So the first column, we say, all right, we've got 4 electron regions, all right? 3 of them are bonding regions, and 1 of them is a lone pair region, right? Because I'm just simply counting up how many of them are bonding and how many of them are lone pair. It's got 3 bonding and 1 lone pair, so it's 4, 3, 1. We go back to our chart, we find 4, 3, 1. Here's 4, 4, 0, 4, 3, 1. So that's that guy right there, and we see that it's a trigonal pyramid. Okay, so this guy is trigonal pyramid. Pretty awesome, huh? Trigonal pyramid. So that's VSEPR. Pretty easy stuff, right? It's not that easy, but it's but once you get the electron dot structure down, figuring out your VSEPR geometry isn't too difficult. Anyway, do lots and lots of practice problems. The only way to get good at this is to do practice. Let me know if you have any questions, and I'll see you on the flip side.